Okay, last video ended a little abruptly, but let's go ahead and finish up the last two results in this section, starting with the so-called extension theorem. The reason this is called an extension theorem is it involves extending a bounded linear operator from a dense set x sub 0 in a norm linear space X, extending that bounded linear operator to all of X. And we'll deal with this by considering some pointwise limits. If we're going to be looking at pointwise limits, we need to make sure we have a complete space in which we're taking those limits, and that's exactly what we have. So the statement is, suppose that x sub 0 is a dense subspace of a norm linear space X, such that t sub 0 is an element of the bounded linear operators from x sub 0 into z, where z is a Banach space. Okay, so the outputs live in a complete space, complete normed linear space, that is a Banach space, and that's where we'll deal with taking limits. And we'll do so in terms of Cauchy sequences. We're in a complete space, so we'll be guaranteed that those Cauchy sequences converge in that Banach space. So that's the setting. The claim is t sub 0 has a unique extension to an operator, capital T, bounded linear operator from x to z. Moreover, the norm of t equals a norm of t sub 0. And if t is an isometry, if t sub 0 is an isometry, then so is t. Okay, so let's look at a proof of this. It's not terribly involved. It does involve a number of cases, though. A number of components, maybe. All right. So we're trying to extend t sub 0 from x sub 0 to t defined on all of x. Our setting is x sub 0 is dense in x, and z is a Banach space. Oh, and all the linear operators are bounded. So take x, lowercase x, to be in norm linear space capital X. Since x sub 0 is hypothesized to be dense in x, then there's a Cauchy sequence, x sub n, subset of x sub 0, that converges to x. Definition of dense is the closure of x sub 0 equals x itself, or everything in x is a limit point of x sub 0. So we've got a variety of approaches, but we get that there's a Cauchy sequence in x sub 0 that converges to this element x in the larger normed linear space. Cauchy sequences converge in complete spaces. All we assumed here is that x is a normed linear space. It's the denseness of x sub 0 that lets us create this Cauchy sequence that converges to x, not the completeness. We'll need the completeness on the other side in Banach space capital Z. So Cauchy sequence, then, for all x sub n and x sub m. In that sequence, we have that t sub 0 of x sub m minus t sub 0 of x sub n in norm equals, it's a linear operator. So the difference of the t sub 0s is t sub 0 of the differences, as it were. So using linearity, we get something of this sort. We've got t sub 0 applied to a vector. You know, in norm, that's less than or equal to the operator norm times a vector norm, as we observed in some stuff we did previously in note 2.4.a. By the definition of operator norm, we get this type of inequality. Since x sub n is Cauchy, then the claim is the sequence t sub 0 of x sub n is also Cauchy. T sub 0 of x sub n, that's a sequence indexed by n. T sub 0 is just some bounded linear operator. And T sub 0 takes these x sub n's and produces elements of Z, the Banach space. But the reason we make the claim that this is a Cauchy sequence, again indexed by n, is because for all epsilon greater than 0, we can make this small. We can make this less than epsilon by making the indices m and n sufficiently large. But if we can make this small, and we've got this inequality, t sub 0, norm of, it's a bounded linear operator, so that's some finite value, then we know that we can make this small. This is finite, this can be made small, so this being less than or equal to that quantity on the right, this can be made small. In other words, for m and n sufficiently large, the norm of the difference here, that is a distance between terms in this sequence, can be made less than epsilon. So some subtle little details skipped. This is Cauchy and can be made small. This is finite. This can be made small. That's the definition of Cauchy in the other setting in Banach space Z. So we got ourselves a Cauchy sequence in Banach space Z. But if Z is a Banach space, it's complete. Definition of Banach space, complete normed linear space. And complete means that Cauchy sequences converge. So we get that this sequence, t sub 0 of x sub n, converges to some element of Z. And that's where we've used the completeness. So the fact that that sequence has a limit, the limit of t sub 0 of x sub n as n approaches infinity, this thing exists as an element of Banach space Z. So take that element and define t of x to be that limit. So as I said, we're using limits, Cauchy sequences, and completeness to find a candidate for the extension of t sub 0 to all of x, from x sub 0 to all of x. All right, so we're defining t of x here. This is the first time in the proof that we've encountered t of x. So we're introducing t of x defined for any x in capital X. We've assigned a value to t of x. Now we need to make sure that t satisfies all the stuff that's claimed for the extension. We need to show it actually is an extension. We need to show it's unique. We need to show it's bounded. We need to show a relationship between the norms here, and finally probably make an observation about it being an isometry under certain conditions. Okay, so it's going to take us a few steps to go through and establish all of this, but they're fairly straightforward. Our first concern is that of well-defined. Now we've defined this t of x using this sequence x sub n that converges to element x. Well, if I used a different sequence that converged to x, would you get the same limit of the t sub 0 of x sub n values? So the fact that this is ultimately defined in terms of a sequence x sub n, we need to make sure that the value, the limit, isn't dependent somehow on that sequence x sub n. That is, we need to make sure this value we've assigned to t of x is well defined. T is well defined, we need to show. That is, we need to make sure the definition of t of x is independent of the Cauchy sequence that we chose. So what we'll do is take a different y sub n sequence of elements of x sub 0 that converges to this point x. And we'll show it produces the same t of x value, the limit of t sub 0 of y sub n, this thing here, this sequence. We're going to show that's the same as the limit of this sequence. We've got t sub 0 of x sub n minus t sub 0 of y sub n in norm, less than or equal to operator norm times vector norm. That's that note 2.4.a, wasn't it? Follows from the definition of operator norm. All right, we've got x sub n approaching x and y sub n approaching x as well. So the definition x sub n approaches x is that the norm of x sub n minus x can be made small. We can make this small. Let's make it less than epsilon over 2 for a given epsilon. Similarly, y sub n converges to x as well, so this can be made small. Let's also make that less than epsilon over 2. So we've got the convergence. So for all epsilon greater than 0, there exists a capital N, and eventually, as it were, such that when the indices are greater than or equal to capital N, we can make both of these things less than something small. Let's make them less than epsilon over 2. Now, for such epsilon and n, consider x sub n minus y sub n in norm. I'm trying to show this converges to 0. Add and subtract x, as we've often done. Use a triangle inequality that produces this kind of thing here. And we ultimately get that x sub n minus y sub n in norm is less than epsilon. So I'm going to put a strict inequality there, probably would be more appropriate, but we get less than epsilon. So the norm must approach 0. In other words, the sequence x sub n minus y sub n must approach 0. So if we apply t sub 0 to x sub n and apply t sub 0 to y sub n, if these vectors approach 0, t sub 0 must map the 0 vector to the 0 vector. So t sub 0 of x sub n minus y sub n, that is t sub 0 of x sub n minus t sub 0 of y sub n, using the linearity of t sub 0, that sequence of vectors must approach 0 also. That is, the sequence t sub 0 of x sub n and the sequence t sub 0 of y sub n must have the same limit. And so the way we define t of x on the previous slide is appropriate. It's t of x is well defined. That is independent of whether we use sequence x sub n, which approaches x, or a different sequence, which also approaches x. So we've got the t of x defined. It's defined in terms of the behavior of t sub 0 on the set x sub 0. We're going from that little dense subset x sub 0 to that bigger set x. Say again, think of this denseness in terms of the rationals being dense in the reals. We might know the behavior of a function on the rationals, and we might be able to use that to extend that function to all of the real numbers. Depends on the function. If it's a continuous function on the rationals, then it'd be pretty straightforward to define it as a continuous function on the reals. And we do exactly this kind of thing here. We look at Cauchy sequences of rationals and so forth. So t of x is well defined. Next claim is t extends t sub 0. What that means is t of x equals t sub 0 of x for all x in x sub 0. Where both t and t sub 0 are defined, they agree. And t sub 0 is only defined on the little subset x sub 0. Think rational numbers. T of x is now defined on all of x. We just need to make sure it agrees with t sub 0 on the set x sub 0. That is precisely this. So this is what extension means. Take x and x sub 0. We define things in terms of sequences. So take the constant sequence, x, 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 x. That's a sequence. It's a subset of x sub 0, because we said x itself is an element of set x sub 0. And then we'll define t of x to be the limit of t sub 0 of x. Treat it as a sequence. It's a constant sequence, so of course its limit is t sub 0 of x. And indeed, t of x equals t sub 0 of x, provided x is in set capital X sub 0. So t really is an extension. Well defined and an extension. We need linear, we need boundedness, and there were some other claims about norms. First for linear, okay? Dealing with linearity means dealing with two things. Let me speak of this in the context of linear algebra. There's vector addition and scalar multiplication, and that's what we have in linear spaces as well. The vectors may be more exotic than what you're used to, and they're prone to be functions instead of n-tuples, but whatever, a vector is a vector. They don't have to be n-tuples. So we'll deal with adding vectors together and multiplying vectors by scalars. So we'll consider these separately to establish the fact that t is linear. All right. You've got t defined in terms of t sub 0, and you know t sub 0 is linear. So we'll just take the question about t being linear and convert it into a question that involves t sub 0. And we know t sub 0 is linear. We'll get the linearity there, and then we'll bring it back to the setting of t itself. So take a couple of sequences, x sub n, y sub n, subset of x sub 0. Let these be sequences converging to x and y respectively. Can be done. Again, x and y are in capital X, and x sub 0 is dense. So you know these sequences exist. Definition of dense. You know the sequence x sub n plus y sub n will converge to x plus y, just property of limits, additivity of limits of sequences. So we can say t of x plus y, by definition of t of something, the definition of t of something is the limit of t sub 0 of something sub n that converges to something, x plus y. We just said x sub n plus y sub n converges to x plus y. So we can take t of x plus y as the limit as n approaches infinity. Throughout these are all about sequences of t sub 0 of x sub n plus y sub n. Definition of t. All right. T sub 0 is linear. So we use the linearity here. T sub 0 is linear. Linearity is being employed there. The limit of the sum is a sum of the limits, provided those constituent limits exist, and they do. This is the definition of t of x. We defined it as a limit. This is the definition of t of y. We defined it as a limit as well, involving a sequence that converges to y. Y sub n converges to y was a setting here. X sub n, of course, converges to x. And so t of x plus y equals t of x plus t of y. There's the vector addition part of linearity. Here comes the scalar multiplication part. For alpha, a scalar, say a real number, t of 0 is linear. So again, we'll take the question about t of alpha of x and turn it into a question involving t sub 0. So t of alpha of x, by definition, is the limit as n approaches infinity of t sub 0 of alpha x sub n. Alpha x sub n being a sequence that converges to alpha of x, still looking at the same sequence that we introduced above. T sub 0 is linear. You can bring that alpha outside of t sub 0. Definition of linear. We're taking a limit here. We can bring alphas outside of limits. Properties of limits from calculus 2, say. And we're left with a limit as n approaches infinity of t sub 0 of x sub n. Well, that by definition is t of x. Since x sub n converges to x, that's the definition of t of x, and so we get alpha t of x, and the scalar came outside. Notice structurally these two proofs are very, very similar. We took it from capital T, turned it into something involving t sub 0 and limits, used the linearity of t sub 0, be it over vector sums or scalar multiplication, and then peeled it apart and took it back to the t setting, still involving the limits. So structurally, very similar between those two pieces. So let's see, t is well defined. It extends t sub 0. It's linear. Let's show the norm of t equals a norm of t sub 0. And part of the claim was t is bounded. T sub 0 is bounded. We started with boundedness there. So this will establish the fact that the two norms are equal. This will establish boundedness of t itself. Now you define the operator norm by taking a supremum over all vectors of magnitude 1. Here, when we're talking about the norm of t sub 0, this is an operator defined on x sub 0. when we take the norm of t, this is an operator defined on set x. So when we do a sup over all unit vectors in x sub 0 versus a sup over all unit vectors in x itself, since x sub 0 is a subset of x, there's more unit vectors here. And so the sup could be bigger. So we get an inequality introduced here, simply based on the definition of operator norm and the relationship x is a superset of x sub 0. So we get an inequality, norm of t is greater than or equal to norm of t sub 0. We need to reverse that inequality. So next, take x, a unit vector from capital X. All right, we can't apply t sub 0 to x, but we can apply it to elements of x sub 0. So take yourself a sequence x sub n of elements in x sub 0 that converge to x. Then t of x, again, x is a unit vector from capital X. T of x is the limit of t sub 0 x to the n, x sub n. That's how we defined t, using a sequence that converges to x. So definition of t. Norm is continuous. Theorem 2.3 said the norm of the limit of a sequence of vectors is the limit of the norms themselves. It was called continuity of the norm. So we can take the norm inside the limit, pick up an equality and equality there. So no inequalities introduced there. Here we've got a linear operator applied to a vector. You know that quantity is less than or equal to the norm of the vector, a norm of the vector times the norm of the operator. But you get an inequality. That's note 2.4.a. Again, follows from the definition of operator norm. That's what note 2.4.a is all about. We did pick up an inequality on that one when we passed to the operator norm. That's a constant. You can take that outside of the limit. Now we've got a limit of the norm of x sub n. We also know x sub n converges to x. So again, by continuity of the norm, the limit of x sub n, norm of, equals the norm of x. Theorem 2.3.c. Oh yeah, and we chose x to be a unit vector. So we can replace that with 1. And we've just shown the norm of t of x is less than or equal to the norm of t sub 0 for an arbitrary unit vector in space capital X. Well, then if we take a supremum of this quantity over all x unit vectors in capital X, the supremum will be less than or equal to this inequality, but the supremum of the norm of t of x, as x is a unit vector, is by definition the operator norm of capital T. So this inequality here implies, upon taking suprema over all appropriate x, the norm of t is less than or equal to the norm of t sub 0. Combine this with the reversal of that inequality, and you draw the conclusion that the norms of the two operators are the same. So there's an establishment that the norm of t equals the norm of t sub 0. Oh, and by the way, kind of some free knowledge from that is that t is a bounded linear operator also. If t is an isometry, then so is, if t sub 0 is an isometry, then so is t. So take x, a vector in capital X, x sub n, a sequence of elements of x sub 0 that converges to x. As always, let's address the norm of t of x. Isometry would mean t doesn't change norms, so you apply t to x and get a vector of a norm equal to the norm of the vector x itself, and that's what we're establishing. How do you define t of x? Limit of t sub 0 of x sub n, where x sub n is given, definition of t. We can take the norm inside the limit, continuity of the norm, as we did previously. We're hypothesizing here t sub 0 is an isometry. So t sub 0 of x sub n in norm is the same as a norm of x sub n, definition of isometry. Same measure, same length. Norms are preserved under isometries. X sub n converges to x, so the limit of the norm of x sub n converges to the norm of x. That's continuity of the norm again. And we've shown t of x and norm is the same as x and norm. X was an arbitrary vector in capital X, definition of isometry. So t is an isometry. Next, uniqueness. T is a unique extension of t sub 0. Okay, well, suppose t1 of x equals t of x for all x in x sub 0. So here we're taking t1 as another extension of t sub 0. It matches t of x, and so it matches t sub 0 of x on the set capital X sub 0. And pick yourself x, an element of capital X that is not in X sub 0. Since t and t1 are both extensions of t sub 0, then they equal each other on X sub 0. We just need to show they're equal off of X sub 0. That is for all x in capital X that are not in X sub 0. Take a sequence, x sub n of elements of X sub 0 that converges to X. You can do that because X sub 0 is dense, right? The hypotheses from the very start, the denseness lets us access all these convergent sequences. Then let's look at T1 of X. T1 of X is defined to be T1 of the limit of X sub n. That's how we defined the extensions. The limit, T1 of the limit is the limit of the T1s. We got continuity here. Yeah, we've got boundedness. We know any extension is bounded. We showed that previously. Let's take a quick look at Theorem 2.6. I think I got it floating around back to the ground somewhere. 2.6. Yeah. Recall 2.6 says if you have a linear transformation between x and y, the following are equivalent: boundedness and continuity. In fact, uniform continuity. You know that extension is bounded. We showed that above when we showed the norm of t equals the norm of t sub 0. So the extension is bounded, and so the extension is continuous. And that's what we're appealing to right here. We're taking a limit in or out of the t sub 1 from this line to this line. That requires continuity. We've even got uniform continuity apparently. But we're good to go with the continuity since, you know, T1 is bounded. We showed these extensions are bounded. Limit. Let's see, we've replaced the T1 with T. Let's see, because the X sub n's all live in X sub 0. So T1 of X sub n and T of X sub n are the same on X sub 0. They're the same as T sub 0 on set X sub 0. So this is the place where we get equality. Now we're dealing with T. Hey, same story. T's bounded since it's an extension. And so it's continuous by Theorem 2.6. And so we can bring the limit in or out of T as well, producing this. The limit of X sub n is X. And that's exactly what we wanted to show. T1 of X and T of X are the same by setting when X is in X sub 0, and by this proof when X, lowercase x, is in capital X, but not in X sub 0. So these two extensions, they're equal, and so we get the uniqueness. They're equal throughout set X, and we're extending from X sub 0 to capital X itself. So there's the uniqueness claim. All right, so here's a statement of the result again, and here's a list of what we've done. So for X and capital X, we've defined T of X in this sense using sequences chosen from X sub 0. We've shown well-defined. T extends T sub 0 in the sense described. T's linear. The norms are the same. In particular, that gives you the boundedness that we're looking for. If T sub 0 is an isometry, then so is T, and we established the uniqueness on the previous slide. So T, and in fact, this is how to define capital T, is the desired unique extension from x sub 0 to all of x. We get the equality of the norms, implying the boundedness. The B there needs to be dealt with at some stage. It's dealt with by this part here. Not only is it bounded, but it's bounded by the same thing that T sub 0 is bounded by in norm. And we established the isometry stuff. So there's the proof of that. No little piece particularly complicated, but a lot of moving parts on that one, granted. All right, back to the current notes. Here we go. So we've extended a bounded linear operator from a dense subspace to a bigger space, provided these were operators into Banach spaces. Without the Banach space stuff for Z, we couldn't have done any of that stuff with sequences. You wouldn't know the sequences converge unless you knew the sequences lived in a Banach space when we were looking at the definition of capital T. A similar idea, different setting, similar idea, similar to the extension of a bounded linear operator from a dense subset to the whole space. We can do the same thing with spaces themselves. We can start with a normed linear space and quote unquote complete it in the sense of having the given space as a dense subspace of some complete space. Shouldn't be a surprise what we'll take as a standard example of that. The rationals have as their completion the reals, but here's the formal definition. Given any normed linear space X, a completion of X consists of a Banach space, X tilde, and an isometry, J, mapping X into X tilde, such that J of X is dense in X tilde. Okay, so we start with a normed linear space. Is it complete? Well, if so, then there's no need for a completion. We'll establish some uniqueness. If it's complete already, it is its own completion. Not a surprise there. But if it's not complete, it can, in a sense, be embedded in a complete space. That is, be embedded in a complete normed linear space. Oh, those are called Banach spaces. So what we're doing with J is embedding normed linear space in this complete normed linear space, in this Banach space. And we're doing so isometrically. Excuse me. So all we've got is norms and linear stuff, vector sums and scalar multiplication. But a large part of the structure comes from the norm in this stuff. And we're preserving that when we say isometry. So J is the embedding of normed linear space X in Banach space, X tilde. And all the old properties of X are preserved in this embedding, in this isometry. Not only that, but we're getting J of X to be dense in the Banach space. For example, the reals are a completion of the rationals. We'll simply take the embedding to be the identity that maps all rationals to the corresponding real number that equals them. And that looks a little weird, but we're simply saying, take the rationals, leave them as is, embed them in the reals. The reals are complete. By definition, they're complete ordered fields. The rationals are not complete. I can find Cauchy sequences of rational numbers that don't converge to a rational number. They'll converge to a real number, though. Take a decimal expansion of the square root of 2 and add successively more digits. That's a Cauchy sequence, but it doesn't converge here. Well, it converges to square root of 2, and that lives here. In that sense, we've completed the rational numbers. They got holes in them. The reals are a continuum, wink, to put it a bit more informally. So what we're doing in some sense when we do this completion stuff is you're kind of filling in all the holes in normed linear space X. The completion theorem states, for any normed linear space, a completion exists. Moreover, the completion is unique, as I mentioned uniqueness a second ago, in the following sense. If, let's keep that definition in front of us, if x1 tilde j1 and x2 tilde j2 are completions, both of x, there is a surjective or onto isometry mapping x1 to x2 such that that isometry, call it U, composed with j1 equals j2. So here's what they mean by the uniqueness. There's a mapping from one to the other. And remember, when we say these are completions, that comes with the fact that completions of x, that comes with the fact that j1 of x is dense in x1 tilde. Right? It says j of x is dense in x tilde here. That's how that corresponds to the claim that this is a completion. And similarly, j2 of x is dense in x2. Definition of completion. Let's look at a proof of that, and that will take care of this section. It's only a couple slides long, so we're almost there. Okay. Let's look at a diagram. If J is an isometry in a general setting, and x and y are different, then the norm of x minus y is greater than 0. The only time you get 0 is when you're dealing with a 0 vector. So different vectors, positive norm. And j of x minus j of y, that is j of x minus y by the linearity of j, equals the norm of j, isometry. So that's the quick way to get to it. J is an isometry by definition. That means j of this vector in norm equals the norm of this vector, x minus y. So we get an equality there. And we said we started this by norm of x minus y being non-zero. So if we take different x and y, then we get different j of x and j of y out. In other words, j is 1 to 1. J is an injection, as the algebra folks like to say. But the isometry says you take different things in, you get different things out. That is, you got an injection, a 1-to-1 mapping. Well, if you've got a 1-to-1 mapping, 1-to-1 function, it has an inverse. J inverse exists. I got to be careful where J inverse is defined, but I do know an inverse of this function exists because we're dealing with a 1-to-1 function. Consider U sub 0 equals J2 composed with J1 inverse. Okay, very suggestive notation here with the sub-zero thing. We're going to use that previous result, the extension theorem, to extend this U sub 0 into the desired U over here. But consider U sub 0 equals this composition. This maps J1 of x into x2. J1 is 1 to 1, so if we take J1 inverse composed with J1 of x, that simply gives x back out. So here's what's going on. All right, here's x, a normed linear space. We're looking for a completion for it. We're going to show ultimately, if we get these two completions, x1 tilde and x2 tilde, then those are the same, unique in this sense of a certain mapping. But here's what's happening. Here's x. In the first completion, we've got J1 mapping x into here. And J1 of x will be dense in here, part of the definition of completion. More of this on the next slide. Same story down here. J2 is a completion of x related to a completion of x. So if we take J2 of x, maps us down here into the x2 tilde, J2 of x is dense down here. So we're dealing with a dense subset of this and a dense subset of that. By name, the dense subset of x1 tilde is J1 of x. The dense set of x2 tilde is J2 of x, definition of completion. So we've taken this, applied these mappings, and got these dense subsets. So let's see, I think before we lose our picture, that's the relevant observation. J1 of X lives here. J2 of X lives here. Maybe one other about this composition. If you'll take J1 of X from here, let's apply J1 inverse. That'll take the dense subset from here, pull it back down to here. That's what this claim here means. Take J1 of X, apply J1 inverse to it. That'll bring you back down over here. And then apply J2 to that. Then J2 will simply take X down to here. So when we look at this U sub 0, J2 composed with J1 inverse, it will map J1 of X back to X and forward to J2 of X. It says here, J1 of X is mapped by this into X sub 2. In fact, as the conversation shows, it's actually mapped onto J sub 2 of X. J sub 2 of X lives down here in this as a dense subset. So what U sub 2 is doing is mapping a dense subset here to a dense subset there. And that's the setting of the extension theorem. J1 and J2 are isometries. So U sub 0 defined to be J sub 2 composed with J1 inverse is an isometry. Pretty straightforward to show compositions of isometries are isometries, and inverses of invertible isometries are also isometries. J2 of X is dense in X sub 2, as I just observed. That's simply the definition of completion. So by theorem 220, the extension theorem, U sub 0 extends to an isometry U from X1 tilde to X2 tilde. So we can use the extension theorem to extend that U sub 0 that maps dense subsets from one place to another place to isometries defined on the whole spaces. X1 tilde plays the role of X in the extension theorem, and the X2 tilde is playing the role of the Banach space, specifically in this application of the extension theorem. Quick observation, we needed boundedness of U sub 0. Its norm is 1. It's an isometry. So isometries have norm 1. So isometries are bounded. All right. X1 tilde is complete. It's the completion of the given normed linear space. The isometric image U of X1 tilde is complete. An isometry will map Cauchy sequences to Cauchy sequences. It'll map convergent sequences to convergent sequences, and it'll map limits of those sequences to limits correspondingly. So since X1 tilde is complete, then U of X1 is also, X1 tilde is also complete. Preservation of completeness, which is described in terms of Cauchy sequences and their limits. But isometries will deal with that as appropriate. So U of X1 tilde is closed in X2 tilde because we've got U of X1 tilde is a subset, subspace of X2 tilde, and it's complete. It's a Banach space. Well, the only time you have a subset of a Banach space, which is itself a Banach space and complete, is when it's closed. And we proved that last video. We proved that in a recent theorem. So subspace of a Banach space is itself a Banach space if and only if that subspace is closed. So we have the completeness, that is, we have the Banach space-ness for U of X1 tilde, so it must be closed since it's a Banach space. U of x1 tilde contains j2 of x. Remember how the mappings go. So this contains j2 of x. j2 of x was dense in x2 tilde. This contains j2 of x. So this, u of x1 tilde, must be dense as well. It contains a set, this set specifically j2 of x, which is dense in x2 tilde. And so u x1 tilde is also dense in x2. But then we've got u of x1 tilde is closed in x2 tilde. It's dense in x2 tilde. The only way you can have a dense set that's closed is to have the whole thing, to have all of x2 tilde. That is u of x1 tilde equals x2 tilde. U we've defined in terms of a composition. Where do we define U? I guess we got it out of an extension related to compositions. We've got U of J1 equals J2 as claimed up here. And in that sense, we've got the uniqueness of the completion. So big deal. We can take any normed linear space and find a completion for it. That's prone to have some applications on down the line. And that takes care of the section on completeness. So a normed linear space is complete if Cauchy sequences converge. If you have a normed linear space that ain't complete, the completion exists out there, and that's what's established in this last result. All right, so that takes care of 2.5. We'll plow into 2.6 next. I will see you there. Have a nice day.